Alright, so I'm going to introduce the chain rule in this video, and then we will have a second video where we're going to do a lot of examples. So what is the chain rule? Or firstly, what would it allow you to compute? So for example, that you want to take the derivative of things of the form, say, e to the x squared plus 2x. How would you address that? We know how to take the derivative of e to the x, but it's not x that we have in the exponent. We have an x squared plus 2x. How do we do that? Or let's say that we want to compute the derivative of the square root of x cubed minus 2. We know how to take the derivative of the square root, but we don't know how to do it when you have an x cubed minus 2. And please do not think about, well, I just take the square root of x cubed and the derivative of 2 separately because the square root of 2 separately because you cannot separate the square root. So that's not a possibility. So what is happening here is that this corresponds to composition of two functions. One function will be the square root of x, and another function will be the x cubed minus 2. Right here, my function, say, on the outside, I want to think about it as I think I'm peeling like an onion, going from outside, working my way in. So the function in the outside is going to be, of x is going to be e to the x, and the function in the inside is going to be x squared plus 2x. So these two functions become the derivative, or these two derivatives rather, become the derivative of f of g of x. And the same here. So we need a rule to address composition of functions. And this is what the chain rule does. And this is one version of the chain rule. There's another one we'll talk about as well. But this is the version that is perhaps more useful to compute derivatives. The other one is good for implicit differentiation and such. So in any case, if you want to take the derivative of f of g of x, or g composed in f of x, then what you would do is you take the derivative of f, you evaluate it at g, and then you pay with the derivative of g at x. So this g prime is kind of like a tax that you're using. So in our particular case, let's say what f prime would be. F prime, if f is e to the x, is e to the x. And then g prime, which I'm going to write at the end, I'm going to have to compute in line because I don't have room for it. But bad planning on my part, but let's go ahead and do it. So the derivative says is f prime, so e to the x, evaluated at g of x. So that's going to be e evaluated at g, so x squared plus 2x in place of x, right? And that's what you would have thought, and I'm not done, by the way, but that's what you would have thought by just looking at it without knowing. You say, well, the derivative of the exponential is the exponential itself, so I just copy it, done. Well, not quite, because you don't have x, you have x squared plus 2x. When you don't have x and you have a function of x, you have to pay the tax, and that tax is the derivative of that function. So in this case, you have to multiply times the derivative of that exponent, 2x plus 2. And that right there gives us our derivative. So it looks very much like what you would have naively thought, but you have to pay up with a derivative of the inside. So let's take a look at this one right here. The derivative of f, as I told you before, is 1 over 2 square root of x. So you would think, naively, that the derivative of this would be 1 over 2, and then instead of just square root of x cubed minus 2, it's just 1 over 2 square root of x cubed minus 2. And you'd say, okay, I leave it at that, right? No, that is your term f prime g of x. You still need to multiply times the derivative of g, which in this case is 3x squared. So let me put some color so we are clear as to what is what. So this here is, or corresponds to, this right here. And in this other problem, this is what corresponds to that g prime. That is the tax you must pay. Now, this other part is going to correspond to this right here. So let's do one more just to make sure that we're getting what's happening. So now we're going to do the derivative of, say, x squared minus 3x plus 1 to the power of something you wouldn't want to FOIL out or distribute out, say power of 7. I mean, sure, you could just do the 7th power, compute it algebraically, get a huge expression, and take the derivative term by term. But why? So here my outside function is x to the 7th, and my inside function is going to be x squared minus 3x plus 1. So the derivative of the outside function is just drop the 7, subtract 1 from the exponent. And the tax, or the derivative of the inside, is going to be 2x minus 3, derivative of this expression. So putting it together, we get the derivative of the 7th power to the 6th times, now this is what you normally would do, just drop the exponent, subtract 1, and here's your tax. And the 3, I did it again. So let me separate it and write it a bit smaller. Just enough to fit it. And that would be your derivative. So in the next video, we'll do many more examples, but this is the idea of our chain rule. So I'll see you in the next video.